Morning, grade 12. Alrighty, a couple of updates. First of all, I want you to know that I have gone onto the assignments tab and I have tried to remove some of our previous assignments. I find it's getting really messy and I have to look with a little bit more effort to find the assignment that we're presently on. However, Teams has no capability to let me hide some of those. If I indeed take them off, they will be lost forever. So although it is frustrating, that's the best way I can have it for now. So please know that I've tried to get rid of the excess assignments just because I find the page really messy. Anyway, number two, I did contact Mrs. Jensen about getting into the school to get some chemicals. I haven't heard back yet. So I'm just going to assume that I still can't get into the building and I will do my best to show you via online videos that I find that are going to be hand chosen by me. I'm going to look for some really, really good ones to show you how a titration actually takes place. Number three, we teachers go back to KVHS building on Monday, June 1st. So depending on how good the videos are that I find online, I can also do a titration for you at that point. No, students won't be in the building, but I can certainly videotape myself in the lab and share that with you. But we'll see how things go. What else did I want to tell you? I also wanted to tell you that this week's assignment is going to be a little bit delayed. A, the holiday threw me off, and B, I wanted to get a little bit further in our acid-base stuff before I gave you an assignment. So I'm going to try and have the assignment ready by tomorrow so that you can have a sneak peek at it at least in case you wanted to see me online during our regular scheduled extra help. But know that I will also schedule extra help Monday and Tuesday next week. So you can also look at the assignment over the weekend and then meet with me Monday or Tuesday live and we can go over different questions too. According to your schedule, we should be starting organic on Monday, but that's not going to happen. So I'm going to steal another day for acid bases. So we will do acid bases today, Wednesday, Friday, and then Monday of next week. And then Wednesday, we will switch to organic. Okay, I think those are all the updates. Now, what I thought we'd start with today is going over questions 5, 6, 7, and 8 from worksheet 5. So worksheet 5 is posted, and we had done the majority of worksheet 5 over our past few lessons. 1, 2, 3, and 4 of part C we did in Monday's lesson, and I'd like to do 5, 6, 7, 8 right now. Correction, I'd like to go over 5, 6, 7, 8 because you did already have those assigned to you for homework. So for question 5, you're mixing ammonium chloride and sodium nitrite in a chem lab. So what you should have started out with first, of course, is the chemical formula for ammonium chloride. And then you should have had that reacting with sodium nitrite and ANO2. And then, of course, you have water present always, always, always. So those were your three chemicals that you started with. And then you would have broken down the ammonium chloride because it's ammonium, it dissolves in water. You would have broken this up because it's group 1, it dissolves in water. You would have left water alone, assigned your acid base, then assigned your strongest acid, strongest base, and you would have noticed your strongest acid is ammonium ion, your strongest base, your nitrite. And when you did the left hand versus right hand, you would have found that your acid was lower on the table than your base. And so that's why we have a less than symbol here, which is a little bit difficult to see, but that's supposed to be a less than symbol. So that means that it's favoring the products. Okay, so this reaction does not want to happen. If I went a little bit fast, then just pause the video and screenshot it. And if you don't understand it, then please reach out to me. The next one, empirical work, that just means lab work, has shown that nitric acid reacts quantitatively, hint, hint, alert, alert. They're giving you a clue there, with a sodium acetate solution. So again, you're writing out the chemical formula for nitric acid, and you're reacting it with sodium acetate. And sodium acetate is NaCH3COO. And then you're having that also mixed with water. And so when you write out those three entities and separate them according to the rules that we went over on, I think it was Friday we went over those rules. Anyway, you would see that nitric acid is one of the strong six, so it breaks apart. So you're going to have H3O plus and your nitrate ion. Sodium acetate breaks apart, water breaks apart, and because they've told us it's quantitative, we know we only have a single-headed arrow in the middle. Okay, so again, pause, screenshot that if you need to. Your next credit assignment will include some of these for practice, okay? Question number 7, a consumer attempts to neutralize an aqueous sodium hydrogen sulfate. Whew, that's a big word. Series of words, cleaner with a solution of lye. And for those of you who don't know, lye is another word for sodium hydroxide. So first of all, we write out the chemical formula for sodium hydrogen sulfate. And remember, hydrogen sulfate is a polyatomic. Na is the sodium, and then HSO4 is the hydrogen sulfate, okay? With lye, sodium hydroxide, and then of course we have our water present. And so then you see what happens when you place those in water. This is going to break up after the sodium. This is going to break up after the sodium, and then the water stays the same. This one you will find actually favors the product, so that should be a greater than sign in there. Okay, so it's pointing to the product. So that means that the acid, HSO4 negative, was higher up on the acid-base table than the hydroxide. So it is going to favor products. It's pointing to the products. Okay, and lastly, question 8, ammonium nitrate fertilizer is added to water. Can it be used to neutralize muriatic acid? So muriatic acid, another name for that is HCl. And they want to know if this ammonium nitrate, if you add it to water, will neutralize HCl. So they want you to have ammonium nitrate present, HCl, which you're trying to neutralize, and then the water. So there's your ammonium nitrate, NH4NO3. You're adding that with HCl. So I have HCl present. And then you're also adding that, of course, to water. So those are your entities. And then what you have to do is see how they're going to break up. Ammonium nitrate, of course, breaks up. It's soluble. Hydrochloric acid is one of the strong six. So you're going to get H3O plus forming from that. And then your water. And what you will notice is that the left side, believe it or not, is the exact same as the right side. So usually what we put in here, which is not very clear, but we say no reaction, okay? Because the left side and the right side are the same. So it's like nothing happened. So no, ammonium nitrate will not neutralize HCl, okay? So by neutralizing, you were hoping to get just water on the right, but nope, that's not true. You're going to still have some acidic component here. So do not use ammonium nitrate fertilizer from your baby barn to try and clean up a HCl spill. Okay, so moving right along. This is from the tail end of last Monday's lesson. I didn't like something I said, at least I think I said. I didn't review my video thoroughly enough to see if I did indeed say what I think I said. Anyway, equivalence point I told you was volume. I'm worried that I told you it was the volume, equal volume of both substances. That's not indeed the case, okay? So the equivalence point, in this particular case, let me just try and find a straight line. So the equivalence point, when you draw a straight line as vertically straight as you can through the pH curve like so, okay? So you can see where that black is hitting the x-axis. That's the equivalence point. So that's probably, I'm going to say about 24 mils of HCl. That is not where the volume of the two substances is equal, okay? And I'm worried that I said that last week, okay? No, That is the point at which the moles are equivalent. There's chemically equivalent amounts of each substance, okay? So the sodium hydroxide and the HCl have reacted and they have chemically equivalent amounts. So that means their moles are equivalent, okay? So that's the equivalent point. How do you tell me that number? How do you tell me where that happened? By giving me the volume of titrant that's been added. Okay, and I'll practice with those terms in a minute or two. The other thing is the end point. The end point is, and I'm going to steal another line here. Let's see, what's a good color? Let's use this green color, okay? That's what this line is, okay? So what you're doing for the green end point, you're looking at the vertical line on the pH curve right here, and you're guesstimating we're about halfway in that vertical drop. So halfway through, so I'm perpendicular to this black line, perpendicular to the equivalent. That's going to be your end point, okay? And that's usually significant or signified, sorry, by a change in pH, a significant change in pH, or by a change in color. So something that you can visualize. So it says in my definitions, a measurable and characteristic property change occurs. So in this case, you'll see the blue change in color. So the solution in the Erlenmeyer will change color. And you'll also see the pH is holding its own about, 13 or so, okay, maybe down to 12. And then all of a sudden, it takes a huge drop, okay? And so we're taking the middle of where that drop is. So just above and just below this curve part, okay? And this unit, of course, talks about the importance of titration. That's a process, and the process in which a precise addition of a solution in a burette is measured into a sample solution. So here is a titration setup. Very precise. These are burettes. There's the word burette. Sometimes you'll see it spelled without the P and the E on the end. That burette is very, very precise. It measures to a volume of 1/100th of a milliliter. So you'll be able to record, let's say, a volume such as this, okay? So to 2 decimal places, okay? So very precise. That's what a burette does. The burette actually starts with a value of 0 at the top, and most burettes will go to about 50 mils. At least those are the ones that we have at the KD High Lab, okay? So it will go to about 50 down here. Now, I'm deliberately putting that lower than where they say the final reading, and I guess I can move this one up too, because you don't have to start your reading initially at 0, and you don't have to finish it exactly at 50, okay? You can use somewhere in between. And I know when I take students to the lab, a lot of time they lose time because they're trying to get this exactly to 0 to start. There's no need, and I'll show you why later. So this is a burette. This is your Erlenmeyer, of course. Whatever you're titrating with goes in the burette, and that's called the titrant. This is a burette clamp. Our burette clamps look a little bit different. Let me just see if I can find you one quickly. Yes, this looks like similar to our burette clamps. So we have some that look like this. They're made of white plastic. And then we also, oh, that wasn't very helpful now, was it? Anyway, okay, some that look like this. Okay, let's see how many times we can do that. There we go. This white. And then we also have some that look like this. Those are metal ones. So if you've seen those in the lab, those are burette clamps. And you can see these two rubber pieces, they will support a burette. So this will actually hold 2 burettes, one on each side. Okay, trying to find one in use. Anyway, so that's what our burette clamps look like. Maybe I should have cut and pasted that little picture. Copy. All right, just so we have it here. Okay, now let me see what else. We do optimize, of course. We do have burette stands, which is shown here in black at the bottom, or ring stands. Okay, these black things here, but we don't often use those because this goes right into our lab bench. Okay, the only thing I do suggest, and I'll mention this later on, if you have a white surface, it's a lot easier to see the color change. So sometimes what I suggest people do is take a white piece of paper and put it underneath the Erlenmeyer. So it's a little bit more obvious to see the color change. So I'm just going to put add paper and I'll put Y. And then that'll be a reminder to you that we add paper because it helps us to better see the color change. All right. In here goes our sample, our analyte, and that has to be a precise known amount. Okay. So in order for that, for the titration to be useful, I guess is the word, we have to know exactly how much of our sample we put in here. So you cannot use a graduated cylinder, okay? You're going to have to use a pipette in order to get that volume, okay? You have to be very precise. Let me put use pipette. Now, I am going to jump over here again and see if I can't find you a picture of a pipette. Let me see. Yeah, so this looks like a pipette. Okay. We're not talking about, and this is a pipette attached to a pump that helps you bring the liquid up. This is actually what we use in the lab right here. So this has your pipette attached to the end of it, and then this is what we call a pipette pump, and it helps us bring up the exact volume. So let me just save this image. So that's what our pipette looks like. Okay, and we have varying sizes of those. So we have 1 milliliter ones, we have 10 milliliter ones, and we use them because they are so precise in their volume. So we're not going to use a graduated cylinder in order to put our sample in the Erlenmeyer because that's not going to be as precise. We're going to use a pipette. And then let me see, P-I-P-E-T-P-U-M-P. And then this is a pump that just draws the liquid up for you or the solution up for you. Let's choose a nice pretty one. Okay, and again, when I show you a titration, I will show you all of those tools in use. Okay, so what do you have to know? You have to know this is a burette. It holds, on average, 50 milliliters, depending on the size you buy, but that's a very common size. Your titrant is in the burette. Your known solution, or sometimes your unknown. It can vary which you put where, but whatever you put in the Erlenmeyer, I should put the word volume here. I think that would be better than amount because I don't want you to confuse that with concentration. Okay, so the exact volume of your analyte goes in here. You know, of course, that's an Erlenmeyer flask, and we do deliberately use an Erlenmeyer flask rather than a beaker because we're going to have to swirl the solution. We're going to have to take it sort of somewhat in our hand, and what we're going to do is put our thumb and our 2 fingers across the neck of it and swirl it. And if we had a beaker, then it could possibly splash solution out, whereas with a narrow neck, it's a little bit easier to keep it contained. Okay, so I think those are some of the highlights that I wanted to talk about on that slide. Now, we talked also about pH curves today and last week, and I want you to know pH curves can only be drawn for quantitative reactions. So quantitative reactions, keep that in mind. That's going to be important later this lesson, okay? Only quantitative reactions will have detectable endpoints, and so therefore only quantitative will be able to be drawn or represented with a pH curve, okay? Because remember, our pH curve is showing a significant drop in pH. We don't have that significant drop, we're not going to be able to draw a pH curve. And that significant drop only happens if you have quantitative reactions, okay? Now, just before we go on, this is showing you the meniscus. The meniscus is this curved surface right here, okay? And that's what happens when you have water in a graduated cylinder, or in this case, we're going to talk about it in a burette, okay? What we have to do is be consistent in how we're reading this volume. So you and all of your classmates and scientists around the world have agreed, yes you have, that you're going to read this volume by looking at the bottom of that meniscus, so the bottom of that curved surface. When you go to read this volume, you should be lining your eye up with whatever number is associated with the bottom of that meniscus, okay? You don't want to read the top up here. You don't want to read somewhere down here. Okay, it's got to be whatever is even with the bottom of that curved surface. Okay, so we're reading right across here. Okay, all right. Now, what I need you to do is take out your notebook and a pen or a pencil. We have 10 minutes and then we'll be at our 30-minute mark. In that 10 minutes, I want to show you just 2 examples. That's it. But I want you to thoroughly understand those 2 examples. We're going to talk about polyprotic substances. Polyprotic substances, okay? So, notebooks out, polyprotic substances, right here. There we go. Polyprotic is your title, okay? Now, here's one example. Here's your second example. And then your homework. All right, so we can do this. All right, example number 1. And if we only get through example number 1, that's fine. I will post the notes as is, and you can follow example number 2. Or I can do number 2, and you can stop listening at 30 minutes. And if I take longer than 30 minutes, you can keep going. I'll leave it up to you. All right, here we go. Let's say, for example, we are titrating sodium carbonate with hydrochloric acid. Okay, so that's what this says. Titrating sodium carbonate with hydrochloric. Now you'll note we have the volume of sodium carbonate and we have its concentration. Okay? Volume and concentration. And the HCl, we have its concentration. Okay? What we're missing here is the volume. Okay? Now, we can solve for that unknown by using titration. Okay? Or usually what happens in most cases, they leave out a concentration and we solve for it. Okay? But with all of these titrations, you're going to have two concentration values, 2 volumes, and one of those 4 will be left out. Okay, now, because we have 25 mils of sodium carbonate, we know the exact volume of sodium carbonate. That's what's going in our Erlenmeyer, because we know its exact volume, 25 mils of sodium carbonate. So that's what I have in my Erlenmeyer, 25 mils of sodium carbonate. And then I'm titrating it with, so that's what goes in the burette, the 0.5 HCl. Okay, now I'm going to put in an indicator, and the indicator they're choosing is methyl orange because based on the chemist's knowledge, the chemist is expecting the endpoint to happen at about 3.8, and methyl orange changes color at that point. Okay, so that's in with the sodium carbonate sample in the Erlenmeyer. Now we're gonna, and here I have white tile, just in case you don't have a white surface or a white ring stand, you're gonna add paper, again, just so you can better see that color. Now, we haven't seen this curve yet, okay? That's what we're trying to figure out, okay? all we're trying to do now is write out the chemical equations that explain this curve. Okay, so if you look at this curve, you should see a bump and a bump. That means there have been two chemical reactions. Okay, whereas if we look above this one, this one bump, one bump, one bump. So there's only been one proton moved. Okay, in this case, there's two bumps. They're weak, but there's two, which means two protons have been moved. Well, if you look at the chemical substance sodium carbonate, you can see there are two sodiums that can be bumped. Okay, in the next example, H3PO4, NaOH, how many protons do you think there are to be bumped there? I'm hoping you guessed 3 because of the phosphoric acid, and you would be right. Okay, now we talked about, well, no, let's look at this one, Na3PO4 and HCl. How many protons do you think there are to bump here? I'm hoping you're saying 3 protons, and so we should have 3 chemical reactions. Okay, all right, so let's go back and do this one right here. So what I need you to write, first of all, is sodium carbonate at the top of your page and HCl. And you're going to do the 5-step Brownstein-Lowry acid-base prediction. Okay, so sodium carbonate up at the top. Maybe I'll do that up here too. Sodium carbonate. Okay, come on, move it up there. Come on. They can't see that tape. Move it up. All right. All right. So there's my sodium carbonate up at the top. Nice and crooked. And then also there I have my HCl because it's in my burette. And also there I have water. How do I know I have water? Because Mrs. Tate said it's in everything, but also because these are aqueous solutions, so you know water is present. Okay, now, a little bit messy, but that's okay. So those are my substances that I'm talking about. Now what I have to do is see what happens when they start to mix together. So I have to do my 5-step rule. So first things first, let's write out those entities. So we have sodium carbonate. This isn't really in the exact order, so let me just do this for you so you can better follow along. Okay, so first we have HCl listed. HCl is one of your strong 6, so I broke it up like so. Sodium carbonate dissolves in water, so I broke it apart like so. And then water. Okay, so you have entities present. So on your page now, you should have these 3 entities, and then underneath, I want you to show me how they broke apart in water. Now, I want you to label the strongest acids and strongest bases. Pause if you want to do this on your own, and then check my work. And then, like the 5-step rule says, choose your strongest acid, choose your strongest base, and have them react together. Nothing there is new. We have done that already. Now, this sodium carbonate means there are 2 protons able to move back and forth, okay? This carbonate can hold 2 protons, okay? So the sodium is a spectator, you're right. So we really don't care about that sodium, okay? It doesn't have any effect on the reaction. But the fact that carbonate has room for 2 sodiums means that this HCl can keep giving off H's and fill those spots for the sodium carbonate. Okay, what do I mean? All right, I'm hoping everyone understood up to this point. You took HCl, sodium carbonate, water, broke them up, choose the strongest acid, strongest base, and then you had the acid give up an H to the carbonate. So you had the acid become water and the carbonate ion become hydrogen carbonate. Now, here's what's important with the titration. And this is a very, very important thing to know. Very important. Look at this titration. How much sodium carbonate did we say we had in this? Correct, 25 mils. Okay, so we put that 25 mils in here, and then we gradually add HCl. That HCl is reacting with that sodium carbonate and forming water and hydrogen carbonate. That's what's in here now. Okay, we no longer have sodium carbonate, we now have water and hydrogen carbonate. So they reacted initially and formed this. That's where we got the first bump. That first H was transferred. Okay, now we know there's a second reaction because there's a second bump. Okay, but there is no longer CO3 2 minus. That CO3 2 minus was used right here, and it broke it. It it received this H. Okay, so I'm going to cover it up. And that's where I start to lose darlings. Okay, so again, let me say it once more. We have 25 mils of sodium carbonate in our Erlenmeyer to start with. That's what they told us. We added HCl to it and it reacted. The sodium and the carbonate broke up and some of the H, the hydronium ion, moved in and took the place of some sodium. So we ended up with HCO3 minus. All of the carbonate that we had listed up here, since it was a strong base, it got used up. It's gone now. So now when we list our entities, we still have the H3O plus and the Cl. Why? Because it's in the burette. We can keep adding more to that burette and adding more and adding more, okay? But we cannot add any more sodium carbonate to the Erlenmeyer. We have a 25 ml sample, the end. So because I can keep adding HCl, I still have HCl in my burette. I still have water because water is present in all solutions, okay? But instead of sodium carbonate, now I have this, HCO3 with a -1 charge, okay? Because some of the sodium carbonate has already broken down. So now these are no longer my entities, these are my entities. So in this first reaction, I formed hydrogen carbonate ion. So the carbonate is all gone. Now these substances are what I'm using here. HCl is a strong acid, so there's where it breaks apart. Water still present, and then your HCO3 minus. And again, we have unlimited supply of HCl. That's why I say lots of hydronium ion, because it's in the burette. Do the same thing again with that. Choose your strongest acid, strongest base, and have the H move back and forth. So you get this. Strongest acid, and now with your hydrogen carbonate, H moves again, and so we have water and hydrogen carbonate. So you can see how when you were itty bitty in grade 11 chem, you would have the sodium go with the chlorine, the hydrogen go with the carbonate, and you would get, I think I said that anyway, NaCl and H2CO3, and that's what I'm proving here, H2CO3. Okay, but it happens in 2 steps. That sodium is lost. Some of the H comes in first and forms HCO3 minus. Then you keep adding more acid, and the second Na spot will be filled. Okay. Now, it says, notice from observing the pH curve, each reaction requires about 25 mils of HCl. And you can see that 25 mils were the first bump, and then about another 25 for the second, okay? The equivalence point, okay? Substances that donate or accept more than one proton are called polyprotic. A carbonate ion is a polyprotic base. This CO3 is polyprotic because it has room for 2 H's. It has a -2 charge, so it's polyprotic base. It can accept 2 H's, okay? Sulfide ions and phosphate ions are other examples. So that's what this slide was showing us, okay? This is oxalic acid. It has 2 H's, so it's a polyprotic acid. This is phosphoric acid. It has 3 H's, so it's polyprotic. polyprotic. Okay, this sulfur down here has room for two H's. It's S2 minus. So that's why we call it polyprotic. Okay, and this phosphate has room to accept 3. So it's a polyprotic base, or you can say this is a polyprotic acid. Okay, now I'm looking at my timer and we're at 35. So I'm going to post all of this. If you want to stop here, that's totally up to you. If you want to stop listening, that's fine. I will go through this one a little bit. This one is from worksheet 6, which we're going to see again on Friday, so you don't have to worry about that for now. This was just showing you strong acid with a strong base with a strong acid. Now look at this one. It starts a little bit higher up than this one, so that means it's not as strong an acid, but it does go up quite high, so it is a strong base. Look at where the end point is, 7. End point, 7. This one, however, the end point is just above 7 because you're dealing with a strong base and a weak acid. So because it's a strong base, the pH after the reaction is done is going to be slightly basic. These are strong and strong, strong and strong. So usually their pH at the end point is about 7. Okay. Now, the next screenshot, have your cameras ready because this is what your homework is. Okay, right here. Here we go. Now, take a deep breath and read that. It's not hard. But usually when I give it to students in class, they have little freak out moments, okay? All we're trying to do is find the pH of 3 unknown solutions. So you have A, B, and C. Here are your clues for A. It has nothing to do with these other two. So just look at solution A, these clues, and find me the pH. Solution B, look at these indicators and the clues and tell me the pH of solution B. And same thing with C. Okay? All right. So you can stop listening here if you want. That is about 35 minutes, 37. Okay? And I'm going to go over example 2 in case other people want to stay on for a little bit longer. So example number 2 is another titration. However, in this case, we're dealing with, let me cover this up just so we can go through it step by step. In this case, we're dealing with phosphoric acid and sodium hydroxide. So you should see there's 3 H's that are going to be transferred to the sodium hydroxide. So we should see 3 curves. We don't though. 1, 2, and then I'll talk about why we don't see the third in a second. Okay, so this is phosphoric acid and sodium hydroxide. We have 25 mils of phosphoric acid titrated with. So again, the with is what's in the burette. So I do have a diagram here for you. So we have 25 mils of phosphoric acid. That's what's in our Erlenmeyer, 25 mils of phosphoric acid. And we're gradually adding sodium hydroxide. So that's what's in our burette. So we're going to have an unlimited supply of the hydroxide ion. Okay. So same thing as before, start out by writing out your entity. So you have phosphoric acid, H3PO4. And there we go. Break it apart as you would expect. So your sodium hydroxide, you break apart. Your phosphoric acid is not one of the strong 6. So you leave it as is. And then your water. Okay. Your strongest base is your hydroxide. Your strongest acid is your phosphoric. Your acid gives up an H, so you're left with H2O and H2PO4 minus. Now, remember a couple of things. First of all, we don't care about this the sodium, because it's a spectator. Now, in the Erlenmeyer, we had H3PO4. That means we have a limited supply of that H3PO4. So when you go up here, that H3PO4 has reacted. It's now gone. okay? It's now gone, whoops, because it has all been used up to form, there we go, it's gone, to form this H2PO4 minus, okay? So it's no longer there. So, X. We started with these entities. We chose the strongest acid, strongest base, and we wrote them here. They reacted and formed this. This H3PO4 is no more. Okay, it got all used up. So, since all that H3PO4 has reacted, the second plateau, this second little peak, has to be because of this H2PO4. So now our entities, instead of having H3PO4, it's gone. We have H2PO4 minus instead. We go through the 5 steps, we choose the strongest acid and strongest base, and we get this. Now, what I did not point out with example 1 is that I'm using single-headed arrows. Because there's a pH curve, we know it's quantitative. This one, again, quantitative, quantitative. Okay, so this is representing the first H. This is representing the second H. Okay, now there's no third one, so that means that this HPO42 minus did not react quantitatively. So when you list out your entities, you have, instead of, now let me just steal this for a second, just be patient. Okay, I'm just going to move this and I'm going to steal something. Okay, I'm going to say, okay,